Well, hello and welcome to this webinar on the technology readiness and costs of carbon capture and storage. My name's Alex Pandas. I'm the General Manager Commercial at the Global Carbon Capture and Storage Institute, and I'll be the Master of Ceremonies for today's event. The work we'll hear about today is part of a broader research program into the opportunities and limits associated with the transition toward a more sustainable global economy that addresses climate change. The framework of this research is the circular carbon economy, which describes a holistic approach to climate mitigation, where every option is utilised to deliver emissions abatement at the lowest overall cost and risk. This work is being delivered through a partnership between the Global Carbon Capture and Storage Institute and the Centre on Global Clean Energy Policy at Columbia University in the USA. And as we publish reports, they will be posted on a website. Their website address is circularcarboneconomy.co. You can see it on the screen now. We're very fortunate to be joined by two excellent speakers who are very well qualified to provide informed perspectives on climate change and carbon capture and storage. Those speakers are Dr. Julio Friedman, a senior research scholar at the Center for Global Clean Energy Policy at Columbia University, and Dr. David Cairns, principal consultant, CCS technology here at the Global Carbon Capture and Storage Institute. Dr. Friedman will make some opening remarks to set the context for today's presentation, and then Dr. Cairns will present the report on technology readiness and costs of carbon capture and storage. And following this, we'll have some time at the end of the session for questions and discussion. So please record your questions in the chat panel, and I'll get to as many of them as I can at the end. Okay, so our first speaker is Dr. Julio Friedman. He probably doesn't need much of an introduction. He's extremely well known. He's a senior research scholar at the Center for Global Clean Energy Policy at Columbia University, as I mentioned earlier, where he leads a new initiative in carbon management. Recently, he served as Principal Deputy Assistant Secretary for the Office of Fossil Energy at the US Department of Energy, where he was responsible for DOE's research and development program in advanced fossil energy systems, carbon capture and storage, and carbon dioxide utilization. He has also held positions at Lawrence Livermore National Laboratory, including Senior Advisor for Energy Innovation and Chief Energy Technologist. Julio has Bachelor of Science and Master of Science degrees from the Massachusetts Institute of Technology and a PhD in geology from the University of Southern California. So over to you, Julio, for some opening remarks to set the context. You have 10 minutes.
Thank you, Alex, and thank you to the Global Institute for having me here. And let me start by congratulating you, David, and the whole team on this excellent piece of work that's come out. It is timely and terrific. In that context, it is a great time for carbon capture and storage. CCS and CCUS have really grown in interest everywhere around the world. And in part, that reflects a shift to a net zero strategy for tackling climate change. And it reflects the growing interest in a circular carbon economy and the need to reduce and remove emissions, as well as adding clean energy sources alone. There remains, I think, a lot of confusion about CCS, and this document helps out a lot. One of those pieces of confusion is that this is a new technology. That is simply incorrect. The first carbon capture plant was fielded in 1938. The first large-scale CO2 injections began in 1972. The first integrated climate-focused project began in 1996. That's the Sleipner project in Norway. And there are easily a half dozen major companies today that will sell you a unit with a performance guarantee, a wrapper at a fixed price. As David will point to, there are now 21 projects operating around the world. They capture 40 million tons of CO2 a year, and 300 million tons total have been captured and stored since we've been doing this in earnest. This reflects, among other things, roughly a 10-fold increase in the tonnage of CCS over the past 15 years, and in fact will see another 10-fold increase in tonnage over the next 15 years, getting hopefully up to something on the order of 400 million tons a year by 2035. Part of the reason why this is happening is, again, net zero as a framework. The Paris Agreement now is operational around the world, 192 countries in every market. There is now no market where carbon dioxide is not an issue and where climate is not a focus. It is also the case that the 1.5 degree report published by the Intergovernmental Panel on Climate Change, the IPCC, that came out in 2018 really shook up the gumball machine. It made people re-examine some of their fundamental ideas. And when you have to get to zero, you got to get to zero. The zero math is clarifying. It means you must reduce or remove all emissions from all sectors. And this is, of course, the subject of our joint report published last year on the role of CCS in net zero. This framing has caused a shift away from the power sector and coal alone, which was where the conversation began 20 years ago, really into all sectors, including heavy industry and, of course, production of hydrogen and air capture. It has also been a focus specifically of CO2 removal. Since we realized that we will now have residual emissions, that there are some sectors for which we have no climate solutions yet, it seems increasingly likely that we will need to remove CO2 from the air and oceans. The first real player in this field was bioenergy with CCS, sometimes called BECCS, which has since moved into new approaches like bikers or direct air capture as pathways. All of this has caused a focus on engineering, and all of this has caused a focus on costs, which are, of course, the focus of this terrific report you've put out and are discussing today. One of the things that we have seen is over the past 10 years, roughly we've seen a 50% drop in costs. This shouldn't surprise anybody because when you field technologies, then you learn stuff. That is a substantial reduction and reflects something on the order of a 10% learning curve, which is similar to other advanced technologies like natural gas turbines, solar panels, and others. This drop in cost has been reflected by growth in market aligning policies. Things like the low carbon fuel standard in California or 45Q in the United States. Even the increases in carbon taxes we're seeing in nations like Canada and Norway, or the growth of price in the European market from their market modifications. All of these things are made possible in part by the drop in compliance costs. We've seen those costs drop substantially in solar and wind. We're seeing those costs drop in real time in batteries. We've seen the cost drop in LEDs. And we are starting to see that cost drop in earnest in carbon capture in a way that has made it policy relevant. I look forward to discussing all of this and more later on in the webinar, but mostly I want to take the opportunity again to underscore the importance of this technology as part of a circular carbon economy and to underscore the timeliness and excellence of this piece of work. Thank you for your attention.
Well, thank you very much for that excellent introduction, Julio. As always, you've done an excellent job in describing the challenges and opportunities associated with reducing emissions and achieving net zero emissions ultimately. A reminder to all of our participants that we will have questions at the end. So if you have any questions at any time, please enter them in the question and answer panel. Okay, let's move on to our primary presentation for the day. Our primary speaker is David Cairns. Dr. Cairns is the Principal Consultant, Carbon Capture and Storage Technology here at the Global Carbon Capture and Storage Institute. His experience spans over 2 decades in the electricity generation, oil and gas, petrochemicals, biofuels, engineering, research, and consulting sectors. David has been a lecturer in process design at the University of Melbourne and in sustainable processing at Monash University. He holds Bachelor of Engineering with honours and PhD degrees in chemical engineering and a Bachelor of Commerce in Management, all from Monash University, which is here in Melbourne, Australia. He's also a Fellow of the Australian Institute of Energy. So David will now present the results of his recent research into the technology readiness and costs of carbon capture and storage. David, over to you. You have 20 minutes and you should share your screen.
Thank you, Alex. Just let me get my screen on. Okay, thank you everyone for tuning in this evening. I'm David Cairns. I'll be talking to you a summary tonight of our recent report on technology readiness and costs of CCS. To give you a sense of what this report was about and some of the messages that we have, in summary, CCS is a vital component of achieving the global goal of net zero greenhouse gas emissions. And importantly, it's going to require large-scale deployment of CCS. And because we're going to be looking at large-scale deployment, that's going to mean there's some significant economic impacts that need to be understood and managed. There are going to be costs involved that need to be understood. All elements of the CCS value chain have costs. So this is CO2 capture, where CO2 is first recovered from flue gas streams in whatever form they are. Subsequent compression or liquefaction of CO2, transport, typically by pipelines or ships, and ultimately to geological storage. There are costs associated with every one of those steps. One element that has an impact on costs is technology development. It's a key driver of cost reductions, especially for capture, but not only for capture. But it's important to realize that technology is not the only driver. We have identified some other drivers that are very important as well. Some of those other drivers include things like the source gas purity, economies of scale, the transport distance, so how far do you have to transport the CO2, the transport mode, so what method are you using to move CO2, the energy costs, the cost of capital, and the cost of storage. To give you a bit of an understanding of how we conceptualize technology and technology readiness, there's a very well-known scale known as the Technology Readiness Level Scale, or TRL. This is a scale that typically runs from 1 to 9. It's a qualitative scale, and it really tries to explain, in a sense, what stage of development a particular technology is. 1 to 3 is describing things that are really being understood in terms of research. So think work that's being done in universities, laboratory scale work, and so on. TRL 4 to 6 is the development of technologies from laboratory system validation all the way through to pilot plants. And 7 to 9 is going to demonstration at large scale. So moving out of the pilot scale phase, and ultimately at TRL 9 being a fully developed commercial product that, as Julio mentioned before, you can go to a vendor and get a fixed price and a service guarantee. And we've got some examples of some different capture technologies here. Things like encapsulated solvents and ionic liquids in the early phase. We have the developing technologies, things like chilled ammonia, polymeric membranes, alum-fed cycle. We'll talk about a few of these later on. And at the demonstration phase, things like amine-based absorption, which is really very mature, certain pressure or vacuum swing absorption processes. And so what we see is that there's not one place that technologies are sitting at the moment in CO2 capture, for example. Technologies are at various stages of development, depending on the particular type of technology we're talking about. To give you a few examples of some of the technologies that are out there, these are some examples for CO2 capture. On the left-hand side there, you have the Veloxitherm rotary temperature swing adsorption process by Svante. Svante is a company that is developing that technology. Temperature swing adsorption has been around for a while. It's essentially using adsorbents or solid particles with an affinity for CO2 to remove CO2 from flue gas streams. But their rotary technology is intended to use that cycle on a much faster basis. What that enables you to do is intensify your asset, get far more separation out of the same amount of adsorbent material you're using. The alum cycle by Net Power is a new power generation cycle that has inherent carbon capture. So effectively, it enables you to produce electricity from natural gas or from gasified coal or fossil fuels, while capturing CO2 in a high purity form as part of it. And a key part of that is that it's using supercritical CO2 as the working fluid for power generation, which is a novel thing to do. Some other examples, modularization is taking off. So modularization is the idea of standardizing and mass producing systems. So we see modularization in a lot of industries over time. Carbon capture is now beginning in the modularization pathway. It effectively allows you to reduce your costs of production by things like mass production. You can share design and drawing, so every plant will be standardized. It won't be bespoke. You can fabricate your equipment off-site. There's an example picture there from Aker Carbon Capture showing you the containerized form of their carbon capture modular technology. So they can be delivered on the back of trucks effectively. On the right, we have the development of potassium carbonate solvents as one of the carbon capture solvents. Potassium carbonate solvents have been around for a very long time. They're very mature, but we're finding even now people are finding ways to improve them. CO2 Capsol has done some innovative work around process design and energy recovery, so making the process more energy efficient. CO2 Solutions Saipem has looked at the use of enzymes to enhance the absorption of CO2 and ultimate reaction into the solvent. And so these are developments of a technology that people may have thought was mature, but with these new spins on them, they're finding ways to make them far more effective. So that's capture. The next component in the CCS value chain is looking at transport. So getting that CO2 from a capture plant, which is generally you've purified your CO2, but it's at low pressure and it typically needs to be pressurized or liquefied to be moved to its destination. This chart here gives you an example of where TRL sits for various aspects of transport. So you'll see that things like compression of CO2 and pipelines, they're very mature. They're TRL 9 basically. Truck transport is the same. So these are very conventional things to do, really not very difficult for us to manage. Where we're starting to get into areas that are needing more development at the moment are things like ship design and ship infrastructure. It's not to say that transporting CO2 by ship isn't being done, because there is a presence of CO2 shipping in the world in the order of 3 million tonnes per annum. But that has typically been done historically for chemical use of CO2, so effectively a utilization. What we're looking at from now on and into the future is bulk shipping of CO2 for storage purposes. And so we're seeing some interesting work emerging from shipbuilders and ship transport companies looking at new models of how do you ship CO2. Pipelines are very, very mature. There's a very well-established CO2 piping infrastructure, particularly in North America, and we expect that that's going to grow rapidly. In terms of shipping, I thought I'd touch on this a bit more because it is underdeveloped at the moment. So bulk CO2 shipping is growing. What you typically see with ship transport of CO2 is that the CO2 has to be in a liquid form. Now, liquid CO2 at moderate pressures, say 8 to 20 bar, is quite cold. It's in the order of -50 to -30 degrees C. And so there has to be some work that's done in the source plant to actually liquefy CO2 before you can put it on the ship. There's some efforts being made in improving and working on the loading and unloading of CO2, not only the loading onshore, but also the offloading potentially offshore. So it's important to note that sometimes the storage site will be an offshore platform operating with an offshore well. And so you have to have the facilities to be able to offload CO2 in those offshore locations. You need, to liquefy CO2, you also need a somewhat higher purity of CO2 than you would need for pipeline transport. So it actually has a direct bearing on the capture technology that you use. You need to pick one that is able to produce a sufficiently high purity of CO2. Not all technologies are able to go for very, very high purities. So it's important to consider this as part of an integrated system. In the face of storage, so the final aspect of CCS is getting the CO2 down into geological storage. The technology development is quite mature in terms of enhanced oil recovery. So this is the process of using CO2 injected into the ground to extract oil from maturing oil fields. That's been operating for 50 years now and has a lot of operating history. In fact, that's really the reason why there's a substantial amount of CO2 piping in the world already. Saline aquifer storage is also mature. It's also TRL 9. It's been done since 1996 for climate purposes. And it's proved that we can inject CO2 into these storages in the megaton ranges. The monitoring has been ongoing for a long period of time and confirming that the storage is indeed permanent. Some of the less mature aspects are things like using depleted oil and gas fields. Technically, they're mature in terms of our understanding. They're just in the case of they just need more development in terms of actual deployments. And then there are areas of unconventional storage, things like basalt storage, enhanced coal bed methane storage. There's no active projects in those areas. They conceptually could be done, but they're not being done just yet. So that gives you a bit of a flavor of technology and how it's developing in CCS. So how does this translate into costs? I guess we'll talk about that in a moment. Obviously, improving technology is typically driven by this desire to reduce the costs and be more competitive. Technology goes so far, but then you need to look at some other factors. Two of the key factors that drive the cost of CO2 capture, so we're back at the capture end of things again. One of them is known as CO2 partial pressure in the source gas. So partial pressure is the volume fraction of CO2 multiplied by the total gas pressure. You multiply the two together, you get the partial pressure of CO2. If you've got a low partial pressure of CO2, basically means you need to have more energy use in your capture plant, which has a direct bearing on operating costs. And you need physically larger equipment typically to do the same amount of capture. That means you need more capital cost. The second factor is economies of scale. So like almost every process technology out there, larger economies of scale means that you get lower costs per unit. This chart here that we produced in-house at the Institute, my colleague Harry Liu produced this one, gives you a little bit of an idea of how these costs vary. So along the bottom here, we have CO2 partial pressures ranging from 1 kPa in the very dilute example of CO2 from aluminium smelter flue gas, moving up to the order of 4 kPa for natural gas combined cycle power generation, maybe up to 12, 14% for biomass and coal-fired power stations, and then getting up into the higher ranges for steel flue gases and cement flue gases. What you can see is that as you move towards the left and you move to more and more dilute applications, the cost per tonne do go up significantly. So that partial pressure is really important. The other aspect is scale. Each one of these bars represents a range of different scales, where the bottom of the bar represents the highest scale and the top of the bar represents a lower scale. So you can see for example, for NGCC, we've got a range of costs here going from the order of sort of $65 up to about $120. This just gives you a sense of, for a range of scales, for the same application, you can see quite different costs per tonne. There are opportunities to reduce capture costs as well beyond this. So modularization, which I mentioned before, that has direct implications on construction time and on construction costs. It also gives you some economies of scale in fabricating the capture plants themselves. So if you can make 100 capture plants, all with the same design, all in a mass production facility, you're going to get lower costs of fabrication. The plant design and drawing costs are also spread over multiple projects. Another way you can reduce costs is through lower energy costs for your project. So we've got a chart here that represents the impact of different energy costs, or different energy supplies rather, on the cost of capture for a range of different partial pressures. The light green line along the bottom represents a zero energy cost. So if you can imagine an ideal world where you get your energy for free. And then as you step up through different energy sources, things like waste heat, heat from natural gas combined cycle. So that's effectively taking some steam out of that cycle, all the way up to a dedicated natural gas boiler. So there's a fairly substantial range of costs that you can incur. And therefore, by choosing your energy supply correctly, you do have an opportunity to reduce costs significantly. Finance and policy support also matter. Things like tax credits, cost of finance. This chart on the right here gives you the impact of interest rates on the cost of CCS. So effectively having an impact on the cost of capital and ultimately feeding through to the cost of capture. You can see that we get this sort of rising arc pattern for each partial pressure scenario. You're seeing that the cost of capital, as it increases from a very low value of 1% up to 15% on the right, can have a substantial impact on the cost of capture. And more importantly, as you get to lower and lower partial pressures, I mentioned earlier that when you've got lower partial pressure, the gas is more dilute, the equipment has to handle larger gas volumes, and therefore the capital costs are higher. That higher capital cost is reflected here by the bigger influence of interest rates on the cost of capture. So you see a bigger influence where the capital influence is higher on the left-hand side. Many projects will also try and offset their costs by getting supplementary revenue streams. So for example, selling CO2 for enhanced oil recovery, also attempt getting sources like capital grants, and sometimes regulation of emissions can provide other incentives as well. Learning by doing is another very important source of reducing costs for CO2 CCS projects, rather. This is an example here on the right of projects involved in capture from coal-fired power stations. What you can see here is that the first project that was developed that was large scale was Boundary Dam, costs a little bit over $100 per tonne. The Petronova project, which followed just a few years later, benefited from a lot of learnings that came out of the Boundary Dam project. So a key part of the Boundary Dam project was knowledge sharing and sharing of lessons, good and bad, that were being experienced in the development and operation of Boundary Dam. And they fed directly through to the design and operation of Petronova. So things like a better understanding of how the plants operate, understanding things like maintenance and integrity practices, including corrosion management, and also looking at improving process design and flow sheeting. Those kind of lessons ultimately flow through from older projects to new ones. And this is a very common pattern. This is not just seen in carbon capture projects, it's seen in process industry projects of all kinds. Moving on to transport costs. Transport costs do not vary uniformly. You get quite different capture costs depending on a range of factors. The first one being scale. So again, economies of scale matter. The second being transport distance, as you would expect, particularly for pipelines. Longer pipelines are going to be more expensive than shorter pipelines. And so therefore, if you're in a situation where your storage site is a substantial distance from your capture source, that's going to have higher transport costs than one where it's right next to the capture source. And also it does have if you have a look at the chart on the right here, it gives you a range of different costs for various aspects of transport. So you can see here for compression and dehydration, depending on the scale. At the bottom here, we've got 5 million tonnes per annum of CO2 at the bottom, 400,000 tonnes at the top. You're getting a fairly substantial range of CO2 costs per tonne. For CO2 transport pipelines, it's an even more stark difference. For very, very high capacity and relatively short pipelines, the costs can be quite low. For lower flows and for shorter pipelines, for longer pipelines rather, the cost can be substantially higher. And we see the same patterns with ships and with CO2 injection as well, that we get these ranges of costs depending on these factors. And so it's really important to kind of absorb the idea that there is no one cost of CCS. There's not even one cost of capture. There's not one cost of transport. There's not one cost of storage. Each of those aspects will have its own unique contribution to make to the overall cost of capture. One of the things that we really sort of have been seeing, and certainly our work has noted this as well, is that there is a really strong incentive for higher scale in transport in particular. The CO2 pipeline bar there, the substantial difference in cost there shows you that there is an incentive to move towards larger pipelines. And so what we did is we actually had a look at that a little bit more closely about what kind of incentive might that engender. In conclusion, really we wanted you to get the sense that in costs of CCS there are several drivers. The dominant drivers are technology development. It's particularly dominant in carbon capture, not so much in the downstream industries, although there is an element of it. The source gas from which the CO2 is captured, its partial pressure of CO2 matters. The scale of capture, transport and storage facilities, so economies of scale matters everywhere. Transport distances matter. And then some of the more prosaic things, as you'd expect, the cost of energy, the cost of capital, and the characteristics of the storage resource. So different storage resources will have different costs of storage. So these factors can all vary widely, and that means that CCS costs can also vary widely. We can see costs lower than $20 per tonne, full chain, in certain large-scale natural gas applications, for example, and could exceed 120 in an example like capturing CO2 from flue gas from an NGCC power station. And so when people ask how much does CCS cost, the answer will always be it depends. There's always this range and variation that we see. And that's it for my presentation.
Okay, well, thanks very much, David. That was a great summary of some very granular and detailed work that you've done to understand CCS technology and understand their costs. Of course, all of that work is in the report, which you can download from the address that hopefully you can see now on your screen, circularcarboneconomy.co/resources. So I guess the answer to the question, how much a CCS costs, David, is it depends.
It depends.
There's never a simple answer, is there? Okay, now we have some time. We have some time for questions for Julio and David, and we have quite a few that have come in. Here's one. Julio, even with cost reductions, why does it remain challenging to deploy capital in the CCS space? And make sure you unmute yourself.
Yes, thank you. So there's a number of reasons why CCS deployment remains challenging, but the primary reason is not one of cost. The primary reason is one of finance. You need market aligning policies in order to deploy clean energy technology. This has proven very successful in the United States and in Europe through things like the Energiewende feed-in tariffs, the UK's contract for differences, in the US, a combination of tax credits and renewable portfolio standards. All these market aligning policies allowed financing of renewable energy projects. In general, CCS has been excluded by law from those same policies. That's beginning to change with, again, policies like 45Q, or with just the increase in economy-wide carbon taxes. CCS is now policy relevant. Unsurprisingly, we are seeing a lot more projects coming off the boards, and that's in part reflected by David's work. The other thing I'll say, and this is something which is systemic and germane to CCS specifically, the financing is often kind of lumpy. You need a lot of capital up front to get going. And in that context, these modular innovations that David pointed to are actually relevant because increasingly it seems that we can get started with these smaller modules and you don't have to amass quite such a large sum of money to get going.
Okay, thanks, Julio. A few technical questions here for you, David. So here's an interesting question. How corrosive is CO2 to carbon steel or stainless steel?
Yeah, another one of those it depends answers. Depends whether it's wet. Depends whether it's wet or not. So if you have water and CO2 together, they form carbonic acid, which is indeed quite corrosive to carbon steel. And so one of the essential parts of the CCS chain is making sure that you remove substantially all of the water, or almost as much as you possibly can, from the CO2 before it goes into any pipelines. We get down to parts per million of water. It's really vital that that's done, because if you get any condensation of liquid water in a pipeline, that becomes obviously a risk of corrosion and something to be avoided. So the solution is dehydration, and that's included in every project. And it's important as well because essentially you've got a situation where the solvents that are used typically for CCS applications are water-based. And so the CO2 that comes out is generally saturated with water when you finish your capture step. So you have to do that dehydration.
Okay, thanks. So Julio spoke at the outset about cost reducing across a range of technologies, CCS being one of them. And you've obviously spent quite a bit of time looking at cost trends in carbon capture and storage, David. What do you think the implications are of what you presented in terms of cost trends for CCS?
I think there'll be a few implications but some of the main ones that come to mind are that we've talked about that there's no one cost of CCS, that the costs really do vary by location. And I think what you'll see is this will have a bearing on where projects get rolled out and the order in which they get rolled out. I expect we'll see projects at the lower end of the cost scale will be deployed first. Those opportunities will be exploited first. So industries like natural gas processing, ethanol from corn, sectors like that have very, very low capture costs. They've got the lowest sort of cost base to start with, but obviously over time, people are going to need to be capturing from higher cost sources. The second one is this intense driver for economies of scale, particularly on the transport side. So we are already seeing the emergence of CCS networks and hubs. So essentially the aggregation of multiple CO2 streams from multiple industrial sources and putting them in shared infrastructure. So shared pipelines in particular really benefit from this. And so this is an opportunity for costs to be reduced substantially. And so that development of shared infrastructure, shared pipelines, shared compression stations, shared storage resources really makes for a much more efficient use of capital and really helps to keep the costs down. So I think hubs and networks is certainly been an emerging trend in recent times. I think that's only going to continue.
Julio, would you like to add to that? I know that's something you've looked at closely.
Thank you very, very much so. This is actually something that is often lost in the public conversation around CCS. When you add renewables into the system, there is already a grid. You make the electrons, you put them on the grid. When you add CCS to a system, there is not the existing infrastructure. The pilot projects that have gone forward now have carried the cost of that infrastructure individually. And that has been a very important limitation. As a solution to this, we are increasingly seeing states and nations paying for some of that infrastructure themselves. The most obvious example of this is the Alberta trunk line in Canada. As soon as the trunk line was built, 2 projects jumped onto it immediately. And I think we're going to see more of that, in particular in the hub and clusters in the United Kingdom, in the EU. We're seeing clusters emerging, Ravenna in Italy, Rotterdam as a port, the Northern Lights project for shipping, the UK clusters. And these will create the dedicated physical infrastructure that will make it much easier to get projects financed and built.
What about clusters that utilize shipping of carbon dioxide? Now, there's a question here from one of the participants about opportunities in Southeast Asia. Mm-hmm. Are you aware of any opportunities in Southeast Asia for long distance transportation of carbon dioxide? I assume using ships mm-hmm. to shared storage locations, and also if either of you could comment on the estimated volume per transport. So how much CO2 is actually transported on a ship?
So I'm really excited to see shipping come up, and the fact that David focused on that with the report reflects how far we've come and how timely it is. We've known that we can ship CO2 for a long time. There just hasn't been a business for it. And so we haven't really done it. The Longskip project in Norway, sometimes called Northern Lights, is in part to validate that business model. The pressures and temperatures, which David mentioned, are basically the same pressures and temperatures for LPG, for liquid petroleum gas, and they're basically the same pressures and temperatures for ammonia. And so as we see growth and interest in shipping in ammonia, we are increasingly seeing interest in backhaul of CO2 using the same ships. And it does not take much modification of the maritime architecture to do that. I do not know of specific projects in Southeast Asia, but I know that all the nations, Singapore, Malaysia, Vietnam, Indonesia, are exploring shipping as a business model. And in part, that is coupled with this pivot to these zero carbon fuels like blue and green ammonia.
David, do you want to add to that? Perhaps talk about the volume of CO2 or the mass of CO2 that's historically been shipped by ships, and what might be in the pipeline?
Historically, the volumes have been quite small because it's really reflected the demand for CO2 for things like beverages and things like that. I think into the future, we'll obviously see those volumes grow as the demand for storage begins to grow. The Northern Lights project, I believe, is 7,500 cubic meters of capacity per ship. So that's of liquid CO2. So that's approximately 7,500 tons, or a little bit less actually. So that gives you a sense of kind of some of these early steps into bulk CO2 shipping for storage purposes. My guess is over time, like all these things, these ships will get bigger as we learn to build them better. Some of it does rely on logistics. So there is a question of, do you have one large ship that sails once a week, or do you have 3 small ships that sail every 2 days? So there will be locations where that kind of sizing of ships and scale will have to be worked out. There's no conceptual reason why they certainly can't get a lot bigger, in the same way that we saw industries like LPG shipping and even LNG tankers getting larger over time.
Thank you very much, David. So there's a couple of questions here which are essentially asking if there is an emerging capture technology that might be a game changer. Are you, David or Julio, seeing anything that you think is really offering very significant performance and cost achievements in the relatively near term?
I don't know if I would say game changer precisely. I mean, there's certainly some exciting ones that offer a lot of promise. I think Net Power's Alum cycle is certainly one that's of interesting, is getting a lot of attention. because of its capacity to do relatively low cost generation coupled with integrated capture. Now that's still in development, and we are yet to see how the exact costs of that come out once the full projects have been built and are up and running. But I think that's one of the ones that comes to mind. Many of the other capture technologies are innovations that are built on what's come before them. And so they're not clean sheet of paper designs. They've taken ideas like absorption cycles or membranes or whatever and made better versions of them. So certainly improvements are happening, but they're generally not step changes. They're generally more incremental. So it's hard to say at this stage which technologies are going to win, for want of a better term. I think you'll see certain technologies will begin to dominate in certain industries. And I think that's really the race that's on at the moment to try and establish themselves as the winner in a particular sector. I think the rewards will be enormous for the companies that can do that.
What about direct air capture? So, 10 years ago, if you spoke about direct air capture, people thought you were losing your mind, quite frankly. Now, how things have changed. Direct air capture is emerging as a real and important option. Julio, I know you've looked at direct air capture quite closely. Would you like to comment on how direct air capture is developing?
Yes, and in fact, this will be a subject of a future circular carbon economy report. I know for a fact that people thought it was stupid because people told me I was stupid 10 years ago when I started thinking about this. In particular, chemical engineers like David were the people who gave me the hardest time. And the reason why is because they said, don't you know that it will take a lot more cost and energy to do this? And the answer was, yes, we do know it costs more energy and money to do this, but we in 2010 already could tell we were going to fail at climate, we were going to overshoot, and that we were going to need this technology. Fast forward, again, the net zero framework is really what has pushed forward a lot of the interest around this. If you look at the total tonnage of greenhouse gases every year, it's 51 billion tons of greenhouse gases. We do not know how to manage about 20% of that. So there's 10 gigatons for which we have no real solution today, or where the solution is like $10,000 a ton. And for those options, direct air capture has roared forward as something that's interesting. It has also roared forward in part because people have begun to understand the practical limits of bioenergy with CCS. BECCS is an interesting technology, but it will not get that 10 gigatons. It's just not going to happen that way. So the good news is that there were a handful of crazy people like myself 10 years ago who started working on this. The best time to plant a tree is 10 years ago, and these people did that. And so we now have a handful of companies that have offerings that are operating in the field. Climeworks and Carbon Engineering, right behind them, Global Thermostat. We have a handful of these companies that are prepared to give you a commercial offering for CO2 removal services with DAC. The prices for that are still very high, typically north of $500 a ton for a price. Those costs and prices, though, have been dropping and dropping rapidly. There's a lot of rich recent literature on this subject, and the consensus estimates for the first megaton plant are between $125 and $325 a ton, so a substantial cost reduction. Again, not a surprise. You innovate, you scale, you drop the costs. Like, we know that recipe pretty well. And so my personal projection is that in 2025, we're going to see the first megaton plant, and we'll know at that point what the price range is. I'll spitball it at about $200 a ton, but I think we're going to see the first plant at about 200. And I think that we will see by 2030 prices in the $150 a ton range for multiple megaton plants. At that point, direct air capture is still not a substitute for anything else. You don't emit today in order to capture later. Like, you still have to rapidly reduce emissions. You still have to get as much as you can today because direct air capture is expensive. But at the end of the day, we will start seeing this deployed, and it will become an increasingly an important part of a solution set.
Excellent. Actually, direct air capture is a really exciting area of development. And as I said, 10 years ago, I thought it was a crazy idea. Now, no longer. It's absolutely part of the solution. Okay, there's a couple of questions here, David, about your cost estimates. One of them asks for your source of information on indicated costs for capture in the operating and future projects with their name? Did you present something with their name? So essentially,
Yes.
what's your source of data there? Are you confident in that data? And there's another question about the numbers you quoted on the cost of capture from, say, NGCC for low partial pressure sources. The view is that they might be a bit optimistic. So perhaps if you could talk briefly about where your source of data is for your costs generally across operating projects, and how you've come up with your range of costs for capture from, say, NGCC. Okay,
sure. The project costs are actually based on publicly available information for those projects. So we've taken information that was available, that was made available for the two projects that have been built and operated thus far, which was Boundary Dam and Petronova. Both of those projects, as a condition of their public funding, were required to publish extensive information about those projects, far more than you would often see from a project of that kind. That gave us some very good insight and direct costs, so seeing exactly how much money was spent on capital, on energy, and various other things. From that, we were able to work out what some costs per tonne were, based on some assumptions around interest rates and so on. The same with the future projects. So there are published estimated costs in those cases because those projects have not been built yet, but the same process. In terms of the estimates that we put forward, they were based on a benchmark study that we did in-house, where we used MEA solvent as a benchmark technology, so that we could really just compare apples with apples. The intent was not to get a perfect estimate of costs for a particular application. The intent was to look at the effects of trends of things like economies of scale and partial pressure. So although you might be able to say, well, for that particular application, there is a project that's got a lower or a higher cost, that's fine because it's probably using a different technology or it's got a particular circumstance or a different cost of energy. We've had to make assumptions there to make it an apples with apples comparison. So they were modeling numbers that we produced internally. And I will note as well that those costs did not include the cost of CO2 compression. So they were capture only. So sometimes people will include compression in the capture cost and sometimes they won't. In those particular examples, they don't include compression. So if you add compression in, those costs will be a little bit higher.
And of course, that's described in some detail in the report itself or in the references, which are
yes, yes, that's right.
The report. Okay, thank you very much for clearing that up. Let me just look through these questions. There's still quite a few we haven't answered here. So Julio, one for you. One of the things that we've seen affect onshore storage projects in the past is the so-called "not in my backyard" effect, where people don't want development near them. How significant do you think that is for carbon capture and storage? So how significant is the potential for community concern to derail a CCS project where storage is onshore? Obviously, it's probably less of an issue offshore.
Well, I would recommend and have recommended to any project developer that they have to take that issue very seriously. They cannot do it as an afterthought. It is important and helpful to engage the public early and have free and frank conversations about this issue. That said, I would remind people there's not one public. Even in California, where there are many communities which have strenuously pushed back on a CCS deployment near them, there are other communities, for example, in and around Bakersfield in the southern San Joaquin Valley, which have actively embraced it, which have campaigned for CCS projects in their backyard. There are examples where in Youngstown, Ohio, communities have fought very hard against carbon capture facilities nearby, and just south of them, 100 kilometers, another community has worked very hard to get it. So I think that it's a real concern, but I don't think of it as an Achilles heel. I think of it as something to be sensitive to manage, and to be proactive about. But fundamentally, the places where we see a lot of CCS developing, like the Gulf of Mexico or Alberta, are places that very much are enthusiastic about CCS. The last thing I'll say is that we are also starting to see in the North Sea development, and in Europe, development offshore, specifically on that basis. Countries like Italy and Germany do not want CCS under their territory, but they are comfortable with it offshore. And we're seeing the same thing in Texas. The state of Texas has just had its first lease sale for carbon capture acreage in the nearshore. And Texas owns, as a state, 10 miles of its coast. So there's quite a lot of pore volume that's in there, and offshore storage is one way to manage that.
Thanks, Julio. So really good question here about which industries CCS can be applied to. As you described, CCS can be applied across a very broad range of industries, effectively anything that's a point source of carbon dioxide. So the question is, which industries would lead in the application of CCS? People are downgrading coal-fired power plants, so will power generation abandon CCS? It looks like steel, cement, natural gas, hydrogen, etc. will lead. What do you think? So which industries do you think CCS will find most application? And what do you think the future of CCS is in stationary power generation? For both of you to answer.
I think I'll go first. I think we've already seen the runs on the board for the natural gas processing sector. It's really forged ahead because, as I mentioned earlier, it's got very low capture costs. So the thing about natural gas processing is you have to separate CO2 from natural gas as part of the processing anyway, and so there's very little in the way of additional costs to take that CO2 and put it into the transport network. So that's really being reflected by the number of projects in that industry. I think hydrogen is going to be another one that's really going to forge ahead. There are plenty of people who like to argue what applications hydrogen may be best suited for, but I think there's no doubt that there is going to be a substantial increase in the demand for hydrogen. The cost advantage that there is of producing hydrogen from fossil fuel sources with CCS is, I think, going to really stand it in good stead going into the future. But I think over time, some industries really have no alternative. If you look at industries like cement, for example, it produces CO2 regardless of its energy source. Even if you ran it completely on biofuels, the process chemistry produces CO2. You're going to have to manage it, and CCS is going to be essential for that industry as well.
Okay, thanks very much, David. Julio, do you want to add to that?
Yes, thank you. I want to remind the audience two things about CCS that are often missed or forgotten. One of them is that all that CCS does is reduce emissions. That's all it does. That's what it does in all the sectors. It just reduces emissions. And so it doesn't compete often with a new energy source. This is just about how rapidly and cheaply you can reduce emissions. This is the second thing. CCS will have a role wherever it is a low-cost option. And so in the power sector, there will be geographies in which CCS plays a very small role, but there's other geographies or markets where it will play a large role. And we're seeing, for example, in China, where gas prices are high, where coal prices are low, where there's a lot of new coal-fired power plants, we will probably see deployment around coal-fired power plants in China. In Europe, where there are more power options like offshore wind, there we're going to see more deployment in the industrial sector because it is the cheapest option there. The value of CCS really is where it is cheap, and where it is cheap, it gets deployed. And that's why David's work is so important, because it's actually pointed out in what sectors it can look competitive against this. The last thing I'll say is that carbon capture and storage has been, I think, cursed or hobbled in some way from day one, in that it has been the only technology in which people look at dollars per ton. Every other clean energy technology has been dollars per kilowatt hour, or dollars per liter, or energy saved. There's been other metrics that have brought to that. And CCS has always started with dollars per ton. In a net zero world, everybody starts to look at dollars per ton for abatement. And part of the interest we've seen is reflected in that. And again, just to be clear, in some options, we're going to shut down plants. In some markets, we're going to shut down coal plants, or we're going to shut down steel mills, and that's just going to be the cheapest option for abatement. In other places, we will replace some generation, say, with zero carbon generation, nuclear in some districts, renewables in others. But in a lot of markets, the reason why CCS keeps coming up is because it's the cheapest option in a bunch of markets, and that persists.
So let me just challenge you a bit on that, Julio, just being devil's advocate. We hear all the time that renewables are the lowest cost source of electricity generation today. So wouldn't it be cheaper to simply switch out all the fossil generating assets with renewable assets? If that were
In some markets, that's true. And in fact, we are seeing that. We saw gas replace a bunch of coal plants, and now we're seeing renewables replacing a bunch of coal plants, and we are seeing renewables replacing some gas plants. Good, emissions go down. That you can't do that yet, really, with a steel mill. There are a couple of projects that are coming forward in, say, Sweden, like the hybrid plant, which are making green hydrogen from zero carbon electricity, a combination of nuclear and hydro, and using that green hydrogen to make a new steel mill. That is an interesting thing, and hopefully we will see that option grow in scale and become an option to replace existing steel mills. In most markets, that facility will cost 2 to 20 times more than retrofitting the steel mill for CCS. In most markets, maybe not in Sweden, but in Indiana, absolutely, that's the case. And that's also true for some of these plants. And even in China, which has great renewable resources and is building out infrastructure and volume just as quickly as it possibly can, in many markets, coal is still a cheaper option. And retrofit with CCS will be a cheaper option there as well. I think this is actually underscores my opening point. The market aligning policy becomes essential. And ultimately, these are government decisions in terms of what gets deployed. And there are good reasons to support renewables, and there's good reasons to replace the fossil generation with renewables. But at some point, it simply becomes more expensive than other options, and CCS is one of those options in many places.
Excellent, thank you, Julio. So I think we'll have one more semi-technical question and then a policy question to wrap up. We're nearly at the top of the hour. So there's a question here about costs of the Quest project, David, in Alberta. Question goes, Quest project in Alberta numbers for CCS I have heard is $60 to $70 a tonne at 95% purity CO2 delivery, including the Alberta carbon prices. That seems much lower than what you are quoting. I wonder why. So can you shed any light on our estimates of the cost, where we got the cost of capture for the Quest project? It's perhaps spend 30 seconds describing for those who may not know what Quest is, exactly what Quest is.
Right, okay. I'd have to go back and dig into some of our old numbers to see precisely what was behind those estimates. I suspect, I don't know, but possibly the costs were on a different basis. That is often the explanation for why you see different numbers in different places, is that the assumptions and what's included and what are not included is the reason for the difference. So I think that's most likely the reason that people, it's very hard to comment when people have heard a number, but you don't know what's behind it. We do have to rely on publicly available information for our assessments. And one of the things that sometimes I think people think we have an inside track on this information. If we do have an inside track, generally speaking, we're sworn to secrecy about it. And so we really, when we make public commentary like this, we do have to rely on publicly available sources for it.
I'll add that the Quest project is at a high concentration source already. It's at a hydrogen production facility in the upgraders. And so that is a lot lower than a power plant capture cost. Yeah, that was, I guess, the other point there is that it's one of the reasons that it was done, I think, was because it was quite an attractive opportunity for CCS. Hydrogen, really, when you look at conventional hydrogen production, say with SMR, there's really two sources of CO2. There's a high concentration source and a low concentration source. The high concentration source is the one that you start with, which is really the process gas separating the CO2 from the hydrogen itself. But you've also got a lot of CO2 that's made when you burn gas to produce heat to actually drive the reactions. That's more dilute CO2, has higher costs. So depending on exactly which CO2 you capture and how much of it you capture, you will get a range of different costs, even within the same facility.
Okay, thanks very much. Okay, so one easy question to round off the hour, and that is, so how do we make this happen? How do we drive investment into CCS at a rate sufficient to meet climate targets? What sorts of policies and initiatives are required to drive that fundamental change?
Well, if I can start with answering that, first of all, it shouldn't be one policy, it's going to be multiple policies. We've seen this everywhere in the world as well. In the United States, we've had renewable mandates plus the investment tax credit, plus the production tax credit, plus the loan program, plus grants in order to get renewable power deployed. All of that was money well spent, but it wasn't one policy, it was multiple policies. And I think we're going to see the same thing here. If I had one and only one lever to pull, for me, the lever I would pull is infrastructure. We really need to get the infrastructure built if we want to see this deployed. And that is rarely a project cost. You know, you don't, if you're developing a project, you don't want to bear the cost for the infrastructure yourself any more than you would want to build your own transmission and infrastructure for a renewable project if you didn't have to. So I think that that's going to be one of the things that will really unlock a lot of projects. But other than that, I think we're going to continue to see market aligning policies, whether it's contracts for differences or expansion of 45Q or high carbon taxes. All of those are going to play a role.
Thanks, Julio. David, do you want to add anything to Julio's comments on policy? I know it's not actually your area of expertise. But...
No, it's not. I think Julio stole my thunder. He said all the things that I would have had in mind anyway. I would add, though, that the transport and the infrastructure side is really important. And I think support for and financing for those transport projects, the pipelines, the shipping, the ports, and so on. I mean, really, the analogy here is if you were trying to run a trucking business and you had to pay for all the freeways your trucks run on, it would be a very different conversation. So I think you'll see far more projects come on board once that infrastructure question is taken care of. And I think even if the users of that infrastructure need to pay for it and there's some sort of cost recovery, that's far more likely to happen than if they have to bear the cost directly and do the projects themselves.
Excellent. Okay, well, sadly, we've run out of time and we really do have to wrap this up. So thanks very much to Julio and David for your insightful remarks and for your excellent presentation, David. Thanks also to everyone who joined us today. We had over 200 people join us for the webinar. It's always pleasing to see good participation in these events. Just a reminder, if you visit the website, which you can see now, circularcarboneconomy.co/resources, you can download David's report plus other reports that are being produced by Columbia University and the Global Carbon Capture and Storage Institute as part of this series. There will be more reports published in the coming months. And watch out for announcements for further reports and further webinars in the Circular Carbon Economy series. There will be more of those as well to go with the report. Finally, if you need any further information on carbon capture and storage, visit our website at globalccsinstitute.com. You'll find hundreds of reports, literally hundreds of reports and other resources that are freely available to the public on our website. And of course, if you're a member, you get a whole lot more. So let's end it right there. I'll say good evening, good morning, good afternoon, depending upon where you are in the world. And we hope to see you on a future webinar. Bye-bye.